All right, so we'll get going here. I know people are kind of creeping in. First, I'm frustrated, so I'll go rant real quick. But would anybody be very upset since there's only, I think I just counted, I think we have 12 or 13 people. If I somehow get us in a room in the business building, would anybody be thoroughly upset about that? No? Okay. I think I might just go on that because this is like week 3.5, 4 on them trying to get them to fix this for me. And I don't know. I'm getting a little frustrated with them. So look for an announcement on Canvas. If they can't figure out something that I can get going here, I'm going to probably see what rooms are available in the business building. I know a few of them that would be, large enough to even get 18 or 19 people in here. And last week or so, that's about what we've had. So I'll put that request in, which, means that we all can't meet at the same time, but about half of you aren't meeting at the same time anyway. So if I can get something set up for that, we may have a room change. If that happens, I'll post it on Canvas. But based off of today, I'm guessing I'm going to try to make that happen. All right, that takes care of that. So the other thing I want to mention before we get going, I put up another Learn Smart up there, and the due date kind of set to read it or kind of go through it before class on Thursday. So we'll talk about some probability stuff today. I really cut that Learn Smart down. It's only targeted time was like 6 minutes, so it shouldn't take you very long at all. Just kind of get on, prime your brain for what we're going to talk about Thursday, because we'll go a little bit deeper into some of the probability stuff that's a little bit trickier. So I don't expect you to have an understanding after going through that, but at least kind of give you a look at that. All right. All right, so we'll get everything going here. Oop, I don't want to do that. All right. So we'll go. Oh, actually, I think I have it sitting in here. I do. I don't know if we'll get there today, especially since we're getting a little bit of a late start. But I also, for this week, posted up an Excel file on Canvas under the in-class data folder. So if we go here, there we go. That union data set, if we don't get to it today, we'll definitely spend a lot of time with that on Thursday. It has nothing to do with the current Excel assignment, but it's kind of stuff that we'll do moving forward. Okay? So for today, jump into these lecture slides. A little bit of a refresher of where we left off. I'm not sure how I'm going to do some of this without being able to, there's no whiteboard in here, or I can't use this dot cam today, but I think I've got some ideas how I can get through some of this. Whatever we aren't able to kind of get a real good understanding of, I'll kind of push that off on the Thursday, okay? So we've got these contingency tables, which I think I briefly showed you at the end of class last time, right? So the way that we read these, we say the total columns represent the probabilities of the events themselves, all right? So the probability of A is 0.6, the probability of B is 0.5, and one way we could reproduce those totals was adding across the rows or down the columns, okay? So I believe it kind of gave a brief idea last time as to why. I'll try to kind of give another visual of this here in just a second. But for now, just know that if you want to reproduce these totals, you can add across the rows. Notice 0.4 plus 0.2 gives you that 0.6. Or if you're trying to reproduce the probabilities of the totals down here, you can add down the columns. 0.4 plus 0.1 is 0.5. 0.2 plus 0.3 is also 0.5. Okay. We also said these top 4 cells represent intersections, right? Or this kind of upside down U, which we said we read as A and B, or A intersection B, okay? So it's outcomes, it's experimental outcomes that occur in both events A and B. So the probability of seeing A and B is 0.4. The probability of seeing something in A complement and B complement is 0.3 here, okay? Now the union we didn't get to, and I'm going to show you a non-technical way to find it, and then by the end of class, I'll show you why that works, and also a couple ways I think it's easier to find the union using these contingency tables. So union, right, this set symbol that looks like a U, means is the outcome in A or is it in B, right? Is it in either one of these, okay? So visually on the contingency table, the way you find a union is you go to the intersection of those two events and you just kind of make an L here, right? You just kind of go one over and one down, right? And if you add those up, that will give you the union of those two events. Right? Now, that is a very non-technical way to remember how to do it. I'll show you in a little bit here why that works, but for now, just know that we could find it that way, right? So 0.2 plus 0.4 plus 0.1, the union of A and B would be 0.7, right? While the intersection, right, was 0.4. Okay? So we'll get a couple probability laws out of the way, and then we'll return to this idea of the union, and hopefully we'll have enough tools to where I can show you why kind of creating that L and adding them up works, right? So if I've got the probability of A or B, that's the same as saying the probability of B or A, right? It doesn't matter if I say, what's the probability I choose someone at random, what's the probability that they're over 6 feet tall and they're over the age of 65? Sorry, over 6 feet tall, yeah, or over the age of 65. It's the same as saying, what's the probability they're over the age of 65 or they're over 6 feet tall? It doesn't matter which way I say that, I'm talking about the same thing, right? Same kind of idea for the intersection. If I want to know what's the probability someone has blue eyes and they have, I don't know, blonde hair, right? It's the same as saying what's the probability someone has blonde hair and blue eyes. It doesn't matter which way I say that, I'm talking about the same thing. So with the intersection, the union, this ordering doesn't matter. Right? We're still looking for the same thing. Now, if we think about the union, that was anything in either one of those circles. The intersection is just the outcomes that are in both A and B, right? So they're in both of those events. Okay? So that was kind of the difference between the union and the intersection, or A or B, and the intersection was A and B. It's kind of a refresher, kind of throwing some new stuff in there. Do we remember when we think about this huge rectangle, visually, what does that represent? It represents every single possible experimental outcome we could see. So we said the area of that rectangle should be what? Does anybody remember? If I add up the probability of every single possible outcome, what should those add up to? 1, right? 100% of, I've looked at 100% of the possible outcomes. Probabilities are essentially percentages, but in decimal form, right? So 100% would be a probability of 1. So that's what this entire experimental outcome space represents. Also, think about the intersection. I was like, when you say it's fine, when it's actually fine, there's almost no intersection there, right? So kind of visually, we're trying to show kind of how much overlap there is between two events, okay? Another one I think I alluded to last class, and here I think is a slightly better maybe way to think about this. If I've got event A complement, we said, is everything that's not in A, right? So if I take everything that's in A, the probability of A, and I add to that everything that's not in A complement, those two should add up to, well, it fills out the entire experimental outcome space. And we just said the entire experimental outcome space has an area of 1. So those two things should add up to 1. So let me see here. Oh, come on. There we go. Put it right above here. Can't write superscripts in here, but the idea would be that if I took the probability of an event and the probability of its complement, those should always add up to 1. Right? And if I just rearrange that a little bit, then I can get that the probability of the complement is just 1 minus the probability of that. So, what if I said the probability that somebody has blue eyes is 0.1, what's the probability they don't have blue eyes? 0.9. How did you do that? Well, probably didn't think through in your head, but you said, well, if the probability of having blue eyes is 0.1, 1 minus that would give me the remaining, right? The probability they don't have blue eyes, right? So that's all this is really saying, okay? All right. Any questions on this before we keep moving? It shouldn't be too bad. So if we want to find the union, right, this is the way I think is preferred, both the way we think about the union, but also once we get to the contingency tables, okay? So if I have the probability of A or B, right, I could be in either one. Let's think about visually what I'm doing. I'm taking every outcome in A. If I added to that the probability of being in any outcome in B, I've essentially double counted whatever's in both of them, right? I think we did an example last class. I kind of talked about a rolling the dice example. When we saw that 3 was in each event, we only counted it once. Well, the problem is if all I have are the probability of A and B here, right? And I can't separate out, you know, what's only in A, right? It's just everything that's in A. I've double counted that intersection. So if I've double counted it, how can I get rid of it? So I only count it once. Well, I just subtract it once, right? Now I've only, you know, if I counted it twice and I subtracted it, I've only counted it once now. So to find the union, so I want to find the union, I'll just add up the probability of both events and subtract whatever's in both of them, right? Whatever I double counted. I think that's an easier kind of intuitive way to think about finding the union here. Okay? Now, another way of thinking about it, a little bit more convoluted, but let's say I wanted to break this down into 3 parts, right? So I want to get first just this crescent moon right here. And actually, can I make my, let's see if I can get, no, I thought maybe I could change the way my mouse looks so it's a little bit easier to see here. But if I want this crescent moon, that's everything that's in A, but not in the intersection, right? So what I could do is say, take the probability of A, so this entire circle, subtract out that intersection. Now I'd be left with just this little crescent moon over here. If I just wanted this crescent moon, that's everything in B, but not the intersection. So I add probability of B, but I subtract out the intersection. So I now have this crescent moon, this crescent moon. The last thing I need to add to it is what's in both of them. Now, if I do it this way, everything cancels, and I get the exact same equation that I had before. So just a different way of thinking about it, breaking it down into 3 parts, as opposed to just adding up these 2 circles areas and subtracting out what I've double counted. But either way, we arrive at this equation, right? The union is the probability of both events and then minus the intersection, okay? So if I'm looking at the contingency table, right, the way I want to think about this is, well, if I said the union of these 2 events, add up the probability of both events, subtract out the intersection, what's the probability of A? 0.6. What's the probability of B? Go down to the total, 0.5. What's the intersection? The probability of the intersection is 0.4. Now it's just a matter of plugging each one of those values in. 0.6 plus 0.5 minus 0.4 gets us that same value of 0.7. Remember I said we could have went to the intersection, made an L, and added them up. 0.2 plus 0.4 plus 0.1 would have given us that same answer of 0.7. Okay? But I think this is a much easier way to do it and a technically much more correct way of doing it, right? So it's very easy to find the probability of the events, probability of A, probability of B in the table. And it's very easy, if we remember those top 4 left cells represent intersections, very easy to find the probability of the intersection there as well, okay? Any questions on any of that? Move this over here. Okay. All right, so this is where it's going to get a little bit tricky. I want to try to show you why, why this works, okay? So if we think about, we've got this union we're trying to find. We're going to really test my drawing skills here today. So let's say I've got this entire experimental outcome space. I give myself a lot of room. Okay? And let's say here is circle A. Here is circle B. So here's circle B. Oops. Here's circle A, okay? I can break this down into 3 parts, right? So this crescent moon, and then kind of this area in between. Now, this area in between, I think that wasn't too bad. We already have kind of identified that as being probability of A. I can't use set symbols here, but the probability of A and B, right? I think that was relatively easy. Now, what would be in this crescent moon here? Well, let's think about, this might get a little bit messy, but let's do blue color here. So if you don't have colors, I'll try to kind of tell you how you take notes with this. So let's think about everything that's not an A, or A complement. Where would A complement be? So if I drew like horizontal lines, everything that's not an A, I'm just drawing, kind of shading in that area that's outside of circle A, okay? So notice this crescent moon over here is everything that's in B, but also is not in A, or is in A complement. Remember, that's kind of what that blue shaded area represents. So if we're thinking about that blue shaded area, think about that was A complement. And here, if I write complement, if you're taking notes, just write A superscript C, right? That's usually how we write it. I'm limited here today a little bit. So, and I could have just, oops. That's not what I wanted to switch off on me. Yes. All right, so you could write this as A complement. So what's in this area was everything that was in circle B, but not in A. Said differently, that's the probability of being in circle B, whoops, and I'll just shorthand this, A complement, right? So I now have this crescent moon, right? That was B and A complement. I have what's in between. Now let's think about where would B complement be? So I'm going to change this to a different color. Let's do, I don't know, green. B complement is everything outside of the circle of B. So if I start drawing kind of vertical lines here, or the green ones, right? Everything that's not in circle B would be shaded in green. Okay? So if I think about this crescent moon over here, that's every outcome that's in circle A, but also in B complement, or not in B. Right? That green shaded area representing B complement. So if I think about this, what's in this crescent moon? I might have to move this here in a second. So that's the probability that I'm in circle A and I'm not in circle B, or I'm in also B complement. Right? So we now have these three different components that altogether, if we add those three up, they would give us the union, right? They'd be anything that's in either circle, right? If we add those three areas up. Well, A and B and A complement, and then A and B complement, right? We can find intersections from the contingency table. So all three of these, is everybody good with this? Can I go back and erase this? Say if you're not ready. Okay. So if we want to find those three components, if I go back here, notice here was the probability of A and B, probability of A and B complement, probability of B and A complement. So that's why adding those three up, making that L, that's why that worked, right? Because what we're really looking for was the three different parts of that union. Now, I think that way is much more difficult to think about and much more difficult to use the contingency table to find. I would suggest anytime we want to find a union using that contingency table, we just remember, just add the probability of the events up and subtract the intersection, right? That was a lot easier to find from that table, okay? But there's two different ways of thinking about the same thing. Right? I want to make sure we kind of cover all of our bases here, okay? Any questions at this point? I'm okay with this? All right. So now that we can kind of think about the union, we know what the intersection is. We're going to talk about a definition, and I think we'll use it a little bit today, but for sure we'll use it on Thursday as well. So this definition is two things are mutually exclusive. Okay? So two events, A and B, are mutually exclusive if they can't happen at the same time. That's the easiest way to think about it, right? So if I said, what's the probability if I selected somebody at random, what's the probability their age is in between 20 and 40? And that their age is in between 60 and 80. That's impossible. There's no age that fits both those categories. So if I've defined events A and B like that, I could never see an outcome that's in both of those events. We would say that means they're mutually exclusive. All right? There's no overlap in these two events, which means the intersection would just be 0. Right? It doesn't exist. That's the lowest probability we could see. We can't have negative probabilities. The lowest likelihood of something occurring would be 0%, or probability of occurring of 0. Right? So if this could never occur, A and B can't occur at the same time, we've got an intersection is 0 there. Now that makes finding the union a hell of a lot easier, right? Because now all I do is add up the probability of each one of these events. I don't have to worry about subtracting what I double counted because I didn't double count anything. Now visually, this would kind of look something like this, right? There's no overlap in our two events, right? Also, if we know that the intersection is 0, that means that on the contingency table, we'd have to see a 0 in this upper left cell, right? Because that represents the intersection of A and B. So anytime I see a contingency table, if there's not a 0 in it, I know that the events aren't mutually exclusive. Anytime I see a 0 in the contingency table, I know that whatever those two events are, they are mutually exclusive, okay? Are we okay with this? It shouldn't be too bad. I think, you know, maybe you've heard this term before or thought about this before. It accidentally slips into my everyday language, which is sometimes a problem. But, right, this is the idea of being mutually exclusive. And it makes this finding the union a little bit easier, okay? So I always give the example, right? If you think about phone and internet access in the 90s, if you only had one phone line, you couldn't actually be on the internet and also be making phone calls at the same time. Nobody even has a phone line anymore. So this is kind of an older example, but this is the kind of a good example of you can't see these two things occur at the same time, okay? All right, so we're now gonna take what we know about the union and we're gonna push to see something, you know, this doesn't necessarily have a specific name to this law, but it's something we can use to find some missing components in certain situations. So first starting off, kind of ignore what's over here. Let's just piece this first part together. If I know this entire experimental outcome space is 1, right, then everything that's in this white area, if I added that to everything that's in this blue area, that would have to add up to 1, right? It fills out the entire experimental outcome space. So what's this white area? What does that represent? Well, that means I'm in either circle A or I'm in B, right? So that's the union of A and B. Now, for now, I'll show you in a second, hopefully, why the blue area represents this. But for now, just take me at my word that this blue shaded area represents the intersection of the complements of those two events, okay? So if I take that, you know, if you take me at my word for that right now, those two things should add up to 1. I then can say, well, look, I have an equation for this union, which is if I just take the probability of the two events and subtract the intersection, that should give me the union. So if I substitute in that equation we had for finding the union, then I know that these 4 components, or these 4 probabilities, also have to add up to 1, okay? So how would I maybe kind of apply this if I actually had some numbers? So first of all, I'll try to give you an idea about why this is the intersection of the complements. So if I go back, where was my blank slide at? Here it is. So once again, we're going to test my drawing skills here. So here's my entire experimental outcome space. If I think about, here's my event A, okay? Might be easier to do it this way first. So let's say I want to think about where's A complement. What we talked about before, that's just everything that's not in circle A. So if I'm trying to like shade that area in black here, or if I don't have colors, I can just use these vertical lines. This represents A complement, right? So these black lines represent A complement. If I then want to think about, I have a second circle, we'll call that circle B, right? Put this text in here, so this is circle B. Where would B complement be? So B complement is everything that's not in circle B. So I just start drawing horizontal lines in the entire area. It's not in circle B. Right? So this red shaded area represents kind of B complement. Okay? If I think about the area now where those black vertical lines or the shaded black area would intersect with the red shaded area, the kind of red horizontal lines here, that's the intersection of A and B complement, which is just everything outside those circles, okay? So that's why when we're thinking about the area outside the union, that's really just the intersection of the complements here, okay? Like I said, not my favorite drawing of this, kind of using this tool, but hopefully this kind of gives a little bit of insight into why that is what it is, okay? So if we go back now, and we just, we use this equation where we know these 4 components have to add up to 1. Now it's really just a little bit of an exercise in algebra. Because I can give you any of those three components or any of those three probabilities, and you should be able to tell me the fourth, right? If I have one equation and one unknown, I can always solve for that, right? So let's say I had a problem like this where I give you the probability of A, I give you the probability of the intersection of the complements, or kind of this light blue area. I give you the intersection of the two events, right? What's in both these circles. But I then tell you, I want you to find for me the probability of B here. Well, it's really just using this equation. We know three of these, plug in those values, and then it's just a little bit of algebra. So if I use that same example, and I use this equation where I know these four components have to add up to 1, I can plug in 0.5 for the probability of A, 0.1 for the intersection of the events, 0.3 for the intersection of the complements. Now it's just a matter of rearranging things and solving for that probability of B. So if I plug all those values in and then solve for B, I basically just have some simple addition and subtraction. What was my screen up there? So the union, the intersection is where they cross. The union means, so think about it this way. A union B, which is that like U, right, or the set symbol. I'll use them, actually, this is actually kind of a good example. So let's say I have two people, right? This person has their assets, this person has their own assets. The union, if they get married, right, a union, now all the assets are in the union. So, right, so it's anything that's in either one. So the union is anything in circle A, anything in circle B, or it could be in both, right? It doesn't have to necessarily just be in one of the events. It could be in both, right? So if we go back, oh, I had a, let me see, oh, there it is. So the union is this entire white area, right? Okay. So anything in circle A, anything in circle B, or anything that's in both of them. So the union includes the intersection, right? The union includes the intersection, which if we look at this equation, right? The union, right, we had to subtract this out because we double counted the intersection. Well, subtracting it out once, it's still in there one time. Does that help? Can I clarify? So the union kind of includes the intersection here. So now, scroll down here. So once we plug all those values in, like I said, it's just simple kind of addition, subtraction of whatever the values that we had there. Now, I kind of skipped all the individual steps of the algebra. I'm assuming hopefully most of us can do that. If you're having kind of issues, I didn't want to like waste class time kind of breaking down every single little algebra step here. But once you plug those numbers in, it's really just rearranging things so that we're solving for that one thing we don't know. Okay. You know, so what does it end up being? 0.3, right? If we actually do this math. Okay. So I'll show you another one. Yeah. Yep. Yeah. Yep. I had it in a different order. Yeah, so let me see. So actually, if I wanted, yeah, I agree with you actually. So I should, what you're saying, you want it to look like this, right? Where the order is the same, where I have the probability of the two events, subtract the intersection, and then add in the intersection of the complements. Yep. Nope, right? It'd just be kind of moving these things. Yeah, it wouldn't make a difference because notice, even when I had that in a different order, the intersection of the two events has that negative sign. The intersection of the complements, we're adding that in. Yep, yep. But yeah, you could, where did I have? I did it. Yeah, you could I could rearrange it so it matches the exact same. But it doesn't matter which order you put those in. I mean, right, once we kind of do the algebra, they kind of get mixed up anyway, so it's not overly important that we have them in that exact same order. Okay. Any other questions? That's a good question, though. Check here. All right. So no, another example, it's the same thing, but maybe I give you three other components, right? So I'm using that same equation, but now I give you the probability of A, the probability of B, and the probability of the intersection of the complements, or A complement and B complement. But I don't give you the intersection of just A and B, right? So now I can think about which of these components do I know? Well, I know the probability of A, B, and the intersection of the complements, and I'm solving for the intersection of the two events, right? So what you could do, right, is first rearrange the equation. So in the other one, I said plug the values in and then do your algebra to solve for what you don't know. If you wanted to, you could rearrange this equation to that first solve for what you don't know and then plug the values in. Right? It doesn't matter which of those steps you do first. So the one thing that I'd say, be careful with when we're kind of doing our algebra, and you kind of pointed this out, but remember, there is a negative sign in front of the intersection of the two events, right? So if I ever end up getting something that's like a negative answer, it's probably because I added it instead of subtracted. I kind of forgot that negative sign was there. Now, if I get a negative value, I know I should have made a mistake because this probability can only be between 0 and 1. Also, if I end up with a probability over 1, I know I probably made a mistake somewhere, okay? So if we plug the values in here, right, we could do some then it just becomes really simple math. Also, so two things here. A lot of people get confused with these Venn diagrams, the way it's displayed. When I write the probability of B as 0.3, it looks like sometimes visually people start to think of just that crescent moon, but really, right, the probability of B, I drag this over, really is everything that's in that circle, right? Everything that's in the circle, and it could be in both circles, right? Could be in that intersection. So the probability of B is this entire circle here, okay? Another thing that someone brought up yesterday, and I don't know, this is one of those things where there's several ways to think about things, and this is another way you could think about solving these. If I am looking for this intersection, well, basically I know that once I add up the other three, the intersection is going to be whatever would get me back down to 1, right? If I'm subtracting it out, if I forget to subtract it out and I just took the probability of A plus the probability of B, so 0.3 plus 0.3, there we go. So you guys hear me now? Test, test, test. Oh, testing. There it goes. All right. Sorry I lost you guys there. I have no idea what happened. It just gave me a bad connection on Zoom there for a second. The fun never ends with technical issues. Okay, so what I was kind of finishing up there was just going through another example where we had 3 of the components and we didn't know the 4th. The thing I had said was someone had kind of brought up to me, if I don't want to use this equation, but I think about if I'm trying to find the intersection of these events, if I just add up the other 3 components, the intersection would be always what has to be subtracted to get me back down to that value of 1. And here, if you add 0.3 plus 0.3 plus 0.5, that'd be 1.1. What we would have to subtract to get back down to 1 would be that 0.1. Okay, just different ways of thinking about that same thing. When I post this on YouTube, if there's some little jumps here, it's probably because I edited this disruption to make things merge a little bit better. All right. So I'm not sure where I lost you guys on Zoom. So are there any questions at this point before we kind of move on? Any questions in here? All right. So this is the one where it's going to get a little bit tricky with my drawing. So I'll try to first set this up so that we just have the idea of conditional probabilities down pretty well. And then I'll try to give you some visuals to go along with it. So I'm going to skip this slide. I'm actually going to work in the reverse of the order I have my slides in because I think intuitively it's a little bit easier to first think about it this way, right? So what we would call this, right, this probability is the conditional probability of B. So I'm still looking for the probability of B, but I'm now conditioning, right? That vertical line is saying I'm conditioning on the fact that A has already occurred. So whatever's on the right-hand side of that line, we're like assuming that we know that we're already in that event, right? We know that that event has occurred. Knowing that that event has occurred, now what's the probability of B, right? So if I'm breaking this down, trying to give a little bit of context here. We would say, if I'm just looking for the probability of B, we call that the unconditional probability of B. Right? If I'm looking for text probability of B given A, right, we say that's the conditional probability of B. Right? So here, I'm not conditioning on anything, so it's the unconditional probability of B. Here, I'm still looking for the probability of B. It's just now I have this additional information. Okay. So the example I kind of give to go along with this is think about, and I don't know, not everyone may have enough knowledge to understand this example, but I'll kind of talk through it to where I think we all will. So I was looking at the other day, there was some survey in Indiana, and the probability, if we looked at what percent of people were in favor of marijuana legalization, it was somewhere in like the 60%. But for the sake of the example, let's say it's 60%. Okay? So our unconditional probability of B, event B being one, supporting the legalization of marijuana, that probability of B is going to be 0.6. Right? But if I then said, okay, what's the probability that if I chose someone at random in Indiana that they're in favor of legalization of marijuana, however, given, right, or conditioned on, I'm already telling you that that person, event A, that they are a registered Democrat, right? So what's the probability that they want marijuana legalized, given that you now know that they're a registered Democrat? What do you think probably happens to that probability? They'd probably be more likely to be in favor of it based off of all the voting records and things that we see. Kind of Democrats tend to be a little bit more left-leaning on kind of our social issues, or kind of, especially on this one, right, if we look at the voting data. So now when I've given you additional information that this person is a registered Democrat, you now know that the probability of seeing event B, that they would vote for supporting the legalization of marijuana, is actually higher than 60%. And if I tell you, well, what's the probability they'd probably vote to legalize marijuana, given that they're a registered Republican? Well, now you think the probability of B is probably a little bit lower, right? So these conditional probabilities, because I'm giving you more information, it's going to impact the probability that this event occurs. Okay? The maybe non-so-political one, the everyday life one that we could use is, if I'm just walking around, what's the probability that I slip and fall? It's pretty low. I don't know the last time I've slipped and fallen, right? I don't slip and fall very often. However, if I give you some additional piece of information, say, well, what's the probability today that I slip and fall, given that we just had an ice storm, right? And that, the roads are, well, the probability raises quite a bit, right? I know when I was undergrad, I can't count how many times I'd see people, slipping and falling, getting off the bus, right? Every time there was like some snowstorm. But that probability is only higher if you give me that additional information that the weather was really bad that day, right? So that's the idea of conditional probabilities, right? I'm just giving you a piece of information that lets you update and update that probability of the event that you're looking at. Okay? So the way that we can find these conditional probabilities, I have this equation here, and I'll try to give you a visual in just a second. But to find the conditional probability, we're just going to look at the intersection of the two events and divide by the probability of whatever I've conditioned on, or whatever that given is, right? Whatever's on the right-hand side of that line. Okay? So I have to clear this for a second because I'm going to put in I'll put it in down here, blank slide. And I'll try to give you a visual as to why that is the way it is. So first of all, where are we at on time? So I want to make sure I don't. Okay, we're good. So let's go here. I'm going to draw an entire experimental outcome space here. All right. Then going to think about, usually I draw these events as circles, but for the sake of this example, I'm going to use squares. It doesn't matter. Shapes don't really matter. It's just, it might be a little bit easier to understand what I'm doing here. So let's say that this lower space is event A, right? And I've tried to draw it proportionally so that it's like exactly half of all the possible experimental outcomes, right? Well, if I think about, so actually, let's keep a running total of what we're doing here. So, probability of A, let's say that's, let me get this to work, 0.5, okay? It's exactly half of all the possible outcomes. If I then think about B, event B, and let's say, this is an extreme example, but let's say that event B is right here, okay? So the way that I have this, remember, A is the entire lower rectangle, but event B is just kind of this smaller one within event A. So here is an interesting example where the entire probability of B is the same as the intersection with A and B, right? Because there's no space where I could be in event B and I wouldn't be in event A, right? So we kind of have this unique example where the probability of B, and the way I've tried to draw this is it's about half of that space. So the probability of B is 0.25, but the probability of the intersection of those two events is also 0.25, okay? Now, if I'm thinking about what's the probability of B, the unconditional probability of B, well, it's just 1/4 of this entire experimental outcome space, okay? This little rectangle is 0.25, 1/4 of the entire space. However, if I'm thinking about what's the conditional probability of B, so if I'm trying to find the conditional probability of B, probability of B given that A has occurred. Well, if you tell me that event A has occurred, I know that the only possible outcomes left are in this lower rectangle down here, okay? So I've essentially taken my possible space from 1 all the way down to 0.5. Right? So out of that space of 0.5, how much of it is in event B? Well, 0.25, right? So my conditional probability would be, if you tell me that I'm in event A, well, now the probability that I'm also in B, right, that B occurs, is just half of that remaining area, right? 0.25 out of the 0.5 remaining area. Now, what did I really do there? What I did was I took where does A and B overlap, or the intersection of those two, and I divided it by the probability of the event that you told me has occurred, or the event that I'm giving you, right? The given, right? You assume that that's already occurred. Okay. So that's essentially what that equation on the other slide was you're just taking the intersection of those two events and you're dividing it by the probability of whatever event you're conditioning on, or whatever event I've told you, right, has occurred. Okay. Now this was a unique example where the probability of B was the same as the intersection here. But what if the probability of B went up to, oh, it's not going to let me, how do I want to edit this? I can go select, there we go. Let's say the probability of B is now, I don't know, 0.35, but the intersection is still the same, okay? So now let's say, I'm going to get rid of this. Now let's think about what if B was right here, right? So I try to draw it out to the same level here where it kind of exactly splits this lower rectangle in half. But now B also includes the outcomes that are up here, okay? Well, if I condition on A, right, screen went out, give us 1 second here in class. All right, if I tell you that we're in A, so given that A has occurred, I've essentially just cut every other outcome out. So you think about it as, how can I do this on here to give you a nice visual? I want to use my hand, but I can't. So basically think about it as, once I've conditioned on A, none of these outcomes are possible anymore, right? I'm just left with this space that's down below this blue box, right? Because once I've conditioned on A, none of the outcomes up here can occur now. So now, condition on A, what's the probability that I see B? Well, now I'm looking at, well, where did B intersect A? And divide that by the entire probability of A, which is exactly what we had before, right? So it doesn't matter if the probability of B now is a little bit larger. What really mattered was, where does A and B overlap? Okay. Like I said, not my favorite kind of doing it here with this draw tool, but I think that gets the idea. Okay. So if we go back, right, that's essentially how we were coming up with this idea, right? That the conditional probability is the intersection of the two events divided by whatever you're conditioning on. Okay. Now, if I rearrange this a little bit, let's say I just multiply both sides by the probability of A here so I can move it to the other side. We get this multiplication rule, which is that the intersection of two events is just the conditional times whatever we're conditioning on. Okay? So I think thinking about the other way, it's a little bit more intuitive. This doesn't quite make as much sense. If we're kind of using this, we're thinking about, well, why is the probability of this intersection here, so seeing something that's in both A and B, well, we first have to think about the only way we're going to see that is if event A occurs, right? And then once A occurs, well, now what's the probability that we also see B, okay? So now that A has occurred, what's the probability that we also see event B occur? I think that it's a lot more difficult intuitively to think about why this holds. I think hopefully with the visuals, it's a little more obvious why this works. And then just rearranging that equation, we could reproduce this, right? So it's really the same equation, just like a little bit of algebra, depending on what we know and what we don't know, which of these two probabilities we know and which one we don't. Okay? I also want to point out here, because it doesn't matter which way we write this intersection, and probably a better way to think about it, there's actually two ways we could find this intersection, right? We could use this conditional probability or this conditional probability, but notice we're still always multiplying by the probability of whatever event we're conditioning on. Right? Another way of thinking about it on this one is, right, if I want to think about the ordering always changes, so I take the conditional probability of the second thing first, right? Well, the probability of B and A is the exact same as the probability of A and B, right? We already said the ordering doesn't matter. And because the ordering doesn't matter, that's why we can use either of these two equations to solve for that intersection. Okay. Any questions on this before we keep moving? I know I'm throwing a lot at you today, but like I said, we'll get more we'll go through more examples of this Thursday, especially when we look at Excel. We'll build our own contingency tables, and I'll kind of re-explain some of this, or kind of give a refresher on it. So we now have, here's a summary of kind of the main rules that we want to remember. So the first one was just this complement rule. I think that was pretty easy. We then had what's called the addition rule, which is how we found the union of two events, right? And I could rearrange that, right, depending on which of these things I know, like whatever probability. Let's say I have any three of these probabilities and I don't have a fourth, I can always find that fourth one. And we now have this multiplication rule, which we can use to find the intersection of events. Or if we have the intersection, but we don't know the conditional probabilities, we can rearrange that equation a little bit so that we could solve for those conditional probabilities. Okay? So it really just depends which one of these we're going to use. It just depends on what information we're given. Right? So if we go back to thinking about contingency tables, right? Let's say I wanted the probability of R1 given C2. So I want a conditional probability. That's nowhere in this table, right? I can't directly grab that from this table because the totals represent the probability of the events themselves, and then these top four left cells all represent the probability of intersections. Okay? But if we use that multiplication rule, we can find a conditional probability by taking the intersection of the two events and then dividing by whatever we're conditioning on. Right? So here, if I want R1 given C2, I'll take the intersection of those two things and then divide it by the probability of what I'm conditioning on, which is the probability of C2, right? So I can rewrite that conditional probability as the intersection of those two events divided by the probability of the event I'm conditioning on, which was C2 here. And now I can find these from the table pretty easily, right? Where's the intersection of R1 and C2? right here, so 0.2. Where's the probability of C2? Will that go down to the total? So 0.5, 0.2 over 0.5 would give me 0.4. Okay? So we can't directly get the conditional probabilities from a contingency table, but we can use this multiplication rule, and we can always find the intersection of those two events and divide by whatever we're conditioning on, right? We're always going to be able to find those from the table, right? Any questions on this one? What if, let's do it. So what if I asked you instead, what's the probability of R1 given, let's go back here, given C1, right? So what's going to change here? Let's, it's probably a little bit small, so let's go to 100% here. Well, now I want R1 and C1, so I'm now going to be looking for the intersection of those two. But now I'll divide by whatever I'm conditioning on. I'm conditioning on C1 here, so I divide by that probably of that event. Now what values get put in here? So what's the intersection of R1 and C1? 0.4, right? So if actually I write this over here and we kind of leave up the old one just for a reference. So 0.4, what's the probability of C1 occurring? 0.5, okay. So just as a reminder, I'm going to go down here. What we had found before was a different conditional probability, right? We were conditioning on C2, but we were in both cases still looking for the probability of R1, right? Well, notice, if I know that C1 has occurred, so I know that C1 has occurred, what's the probability that I see R1? Well, the only thing left, once I tell you C1 has occurred, the only possible outcome is that I'm in C1 and R1, or I'm in C1 and R2, right? Now, the entire space of C1 is 0.5, and of that entire space, 0.4 of it is in R1, right? So we can kind of think about 0.4 out of the 0.5, right? And that was the probability. Once I know C1 has occurred, the probability I'm in R1, well, is just 0.4 out of that 0.5. Or I guess I'm going to complete this, right? That calculates to being 0.8. Now I think about the conditional probability. What's the probability that I see R1 occur given that C2 has occurred? Well, if I say now I know C2 has occurred, which has the same spaces as C1, 0.5, but now of that 0.5 space, only 0.2 of it is R1. So now it's only 0.2 out of 0.5 would be the probability that I see R1 occur. Come on. All right, so kind of notice there, if we condition on different things, those conditional probabilities can be very different, right? And that kind of makes sense. If I'm giving, if C1 and C2 are that I'm a registered Democrat or Republican, the likelihood that I'm going to vote a certain way on a certain issue is going to change dramatically, right? And that's all we're really saying with conditional probabilities. Okay. Any question here? Because I know I kind of changed and moved some things with the slide. Okay with this? Okay. Let me check here. All right, we're good. So, with this in mind, now that we kind of have these conditional probabilities, we can start to talk about another definition, right? Which is that the idea of independent events, okay? So we say that two events are independent if the unconditional probability, right? So this, we're not conditioning on anything. So the unconditional probability of A, if that's equal to the conditional probability of A, once I'm conditioning on B, then those two events are independent. What this is really saying is, if you give me this additional piece of information that event B has occurred, that doesn't change at all the underlying probability of A. So if you go back to like my slipping and falling example, I said that the probability I slip and fall changes dramatically if you give me this additional piece of information that it's like snowy and icy outside. However, if I'm asking what's the probability that I slip and fall in here in this room, and then I give you the additional piece of information that it's icy and snowy outside, Well, that doesn't affect at all if I slip and fall in this room. And so that additional piece of information wouldn't change the probability at all. And that's because those two events would be independent. They don't depend on each other. Me slipping and falling in this room right now, walking up, getting out after class, has nothing to do with what the weather currently outside is right now. Okay? So the idea of independent events, or that having this additional information doesn't impact at all the underlying probability of the event that I'm looking at. Okay? All right. So if those two events are independent, one thing that becomes kind of nice is if I go back to my multiplication rule, notice if I want to find the intersection of two events, I said that was the conditional probability times what I'm conditioning on. Well, if A and B are independent, what is the probability of B given A also equal to? Well, that's just the probability of B. These are independent. It didn't change the probability at all. So I could actually plug in the probability of B here, and finding the intersection of those events becomes a little easier. I don't need a conditional probability anymore. I just need the probability of the two events, A and B. But that's only if they're independent. Right? And if they are independent, I could check to see if this holds by using that equation. Right? If the probability of A times the probability of B is equal to their intersection, then we would also say they're independent events. Here's the actual definition of what an independent event is, but because of that, we can check to see if they're independent by seeing if this would hold as well. If the probability of A times the probability of B is equal to the intersection, we'd say they're independent events. If they're not, if that's not equal, then we would say that they're not independent events. Okay? So this is kind of our kind of one equation we could use to check for independence. Okay? So let's think about if I had a contingency table, how would I use that to check for independence? Right? Well, here's my definition, right? And it doesn't matter which way I check this, right? If A is independent from B, B is independent from A. Okay? So let's go down here and think about how we could check this using the table. So I can get the probability, which way to do it here first? Yeah, I can get the probability of A from that table pretty easily, right? It's 0.6, okay? So I know the unconditional probability of A is 0.6. How can I find the conditional probability of A? Well, I'm just going to rewrite that as the intersection of those two events divided by what I'm conditioning on. Okay. What's the intersection of the two events? 0.15. What's the probability of the event I conditioned on? Or probability B, 0.25. Plug those in, I get 0.6. Sure enough, that's the exact same as the unconditional probability of A. So here I would say, those two events are independent, right? Because the conditional and unconditional probability end up being the exact same thing. Now, if I had checked it the other way, so let's say I look at the probability of B. The probability of B is what? 0.25. So the unconditional probability of B is 0.25. Well, what's the conditional probability? Well, once again, I can rewrite that as the intersection of the two events divided by whatever I'm conditioning on. What's the intersection of the two? 0.15. What's the probability of A? 0.6. 0.15 over 0.6 is 0.25, which is the exact same as the unconditional probability of B. Right? So, we have to do a little bit of work using the values in the table to come up with these conditional probabilities. But once we have the conditional probabilities, we're just checking to see if they're equal to those unconditional probabilities. So either way we had checked it here, we would have found they're independent. Like I said, if A is independent from B, B has to be independent from A. Okay? Any questions on this? Any concerns? All right with it? So there's one other way we could check to see if they're independent, which is I said, if they're independent, this equation should hold, right? I should just be able to find the intersection by multiplying the probability of each event by itself, right? Or by each other, sorry. So if I take the probability of A here, that would be 0.6 times the probability of B, which is 0.25, right? So 0.25 times 0.6 is 0.15. If that's the same as the intersection of the two, then we say they're independent. Sure enough, the intersection of A and B is also, right, 0.15, okay? So if we use this equation to check independence, we come up with the same conclusion. So really there's three different ways we could have checked independence for independence using that contingency table. Any questions on that before we keep moving here? Sort of wrap things up here in a little bit. Okay. One thing, I wanted to mention something here. Let's think about this, and then I'll move on. So when we're using these two ways to check it, if I think about, without any information, what was the probability that A occurred? Well, probability A occurred was 0.6, and the probability A didn't occur was 0.4. So 0.6 out of the entire space of 1, right? Well, once I conditioned on B, the space is down to 0.25. So I've went from a space of 1. Now I know that I'm in this experimental outcome space that only has a probability of 0.25 of occurring, right? Once I said that, given that B has occurred. Out of that 0.25, right, of that space, 0.15 of it is in A. So 0.15 out of the 0.25 was also in A, which ends up being also kind of 60% of the remaining space, or a probability of 0.6. So it was this idea that just because you tell me that B has occurred, of that remaining space, it's kind of the same proportion of event A as the entire experimental outcome space was. So let's think of an example here. I think I use this example, and I'm sure there's like a biology major or someone that would tell me I'm wrong, but I think this is true. So, I mean, I would assume it's true. If I asked you for what the probability that somebody has blue eyes is, let's say, I think earlier I said what, 0.1 or something like that? Well, what's the probability they have blue eyes given that they're a registered Republican? Probably that shouldn't have any relation to each other, right? So if I think about every single person, that's the entire experimental outcome space, the proportion of people that have blue eyes out of the entire population will be the exact same as the proportion of people who have blue eyes if I'm just looking at registered Republicans, right? That proportion I can't imagine it would be any different, right? If someone told me that, like, I don't know, having blue eyes is, makes you more likely to, be a certain political way, I'd be very surprised, right? So it doesn't change at all the makeup of that remaining group once I've conditioned on that event B of that they're a registered Republican, right? So that's kind of the idea of independence here. So we checked independence. Oh, I'll mention this. We're not going to probably do anything with this moving forward, but it is an interesting byproduct. If two events are independent, what ends up being true is their complements are as well. So actually, if you just took the probability of the complements, that should also be the same as the intersection of the complements. That ends up actually always holding as well. So there's technically another way in which you could check that. We're not really going to use that in any way, but that is an interesting kind of byproduct of independence, that the complements are also independent, okay? So if we have independent events, this is pretty applicable to some real world issues. So let's say, I'm flipping a coin, right? And the probability that a coin comes up heads is 0.5. So over the long run, if I flip a coin enough, I know that probability I see a heads is going to be 50%, right? If I flip 1,000 coins, I'm going to see right around 500 of them come up heads and around 500 come up tails, if it's a fair coin. Okay? So because coin flips are independent, right? If I flip a coin, the probability I see heads on the first coin flip is 0.5. Given that I see a heads on the first coin flip, what's the probability I see a heads on the next coin flip? Well, these are independent flips. I'm flipping it the same way every time. On that second flip, the probability I get a heads should just be, well, if I flip a coin, what's the probability it comes up heads? 0.5. If I got a heads on the previous one, does it change that probability at all? No, those two events are completely independent. So because of, something that people fall victim to is that, like over the long run, I'll see 50% of heads, right? But just because I saw a heads on the first one doesn't mean that I have to now see tails on the second coin flip, right? The underlying probability has remained the same, right? Because these events are independent, okay? So the definition of independence is sometimes, people fall victim to thinking that, the probability comes up heads in that second coin would have to be lower because it has to balance out. Well, not if these are independent events, right? And if we look at people's gambling habits, they fall victim to this what we call kind of I said Kenny Rogers, but it's the gambler's fallacy, which is that just because I see certain outcomes on the previous coin flips, it doesn't change at all the underlying probability of the current coin flip. Okay? So the idea is if I see like 5 tails in a row, that doesn't mean that the next coin flip has to be a heads. Right? Each coin flip is independent. Okay? So the answer here would be like no. Right? It doesn't matter how many tails I get in a row. The probability I see a heads is still 0.5, assuming we have a fair coin. Right? So you can like reproduce this. One time I like got into the weeds here a little bit and did some simulations in Excel, and you can kind of see it doesn't matter how many previous or consecutive tails that I got, the conditional probabilities, right, on these different numbers of streaks of tails, the probability that that next coin flip came out heads is always right around 0.5. Now, it's not exactly 0.5 because I couldn't do this an infinite number of times, but you can kind of see here, it doesn't matter how many tails I previously had. On the current coin flip, the probability I get a heads is always going to be 0.5. Okay? I think we'll end kind of with this story. It kind of relates to this. So I said people fall victim to this a lot. If you kind of ignore the green space for the sake of this example, like if you're spinning a roulette wheel, I don't know how many of you have been, I don't know how many of you have been in a casino or whatever, but you know, it's about 50% black, 50% red. So anytime I spin this, there's a 50% chance that it comes up black or a 50% chance it comes up red, right? Approximately. So back in, 1913, black actually came up 26 times in a row, right? So people fell victim to this gambler's fallacy, and after like the 10th time it came up black, they're like, well, it's come up black 10 times in a row. It has to be red in the next one. Well, no, if it's just a fair wheel, the probability it comes up on black or red again is 50%. But people fell victim and said, well, it's been red or black 10 times in a row. It has to be red now. And they started putting all their money on red. Well, after 10 times, it still hit black another 16, right? 26 times in a row. And kind of, the casino made tons of money off of this, right? Because people just kept putting money on red and then losing. Even though every single spin, it was just a 50% chance each time. So they should have been betting as though it was a 50% chance. We see this a lot in kind of sports betting as well, that people will kind of follow these gambler's fallacy behaviors. We're kind of running out of time there. So I think I'll kind of leave it with that example. But knowing that the underlying probability doesn't change if events are independent becomes very important when we're looking at some of these real world applications. So we'll pick up with conditional probabilities again next class. We'll do some work in Excel. I think here, we'll start in Excel. We'll build our own contingency tables. So we'll get more work with these contingency tables, more work with conditional probabilities in this multiplication rule. Look for an announcement, especially tomorrow. I doubt I'll have an answer today, but look for an announcement on Wednesday or early Thursday about possibly moving classroom locations because I'm a little fed up. So if there's any questions, email me. I've met with some students via Zoom on that Excel assignment. I think it helps quite a bit. Other than that, good luck on that, and I'll see you guys on Thursday.